So today we're going to look at section 3.2, which has to do with logarithmic functions. So we're going to talk, we're looking at exponential functions and logarithmic functions. They kind of go hand in hand a little bit. So the question I have for today is, does an exponential function have an inverse? Well, if we were to draw an exponential function, and we're just going to randomly pick one, I'm just going to pick an exponential growth. We know that it's going to look something along this line, right? So anytime we want to find out if a function has an inverse, we always test it by using the horizontal line test. And if the function passes the horizontal line test, then we know that the function has an inverse. So when I look at my function and I go through and I make these horizontal lines, no matter where I cross over or make those horizontal lines, I'm only going to cross the graph once. Even here, I'm getting closer and closer and closer to 0. I'm never going to reach 0, but I'm going to get closer to 0. So I'm still going to pass that horizontal line test. So does it have an inverse? Yes, it does. So what is the inverse of an exponential function? So what is the inverse? You may have already guessed it. It is a logarithmic function. So if we think of our exponential function, and we can write our exponential function, if we want to write it as f of x, it would be f of x equals some base raised to the exponent, right? So a lot of times we can write that as y equals some base raised to some exponent, and we know for it to be exponential, our variable has to be in the exponent in which it is. So we can remember back when we had to find inverses, and to find an inverse, you switch the x and the y, and then you solve it for y, right? So to find the inverse, I would switch the x's and y's, so I would now have x equals b raised to the y. So now I need to figure out how to solve it for y. Well, I have a little issue, don't I? Because my y is up in my exponent, and I really don't know how to get rid of it or how to get out of it. So this is where some little rules come into place, and we can swap back and forth between logarithms and exponentials. So we can take an exponential function, or anything written exponentially, and this is written exponentially because y is in the exponent. I can now rewrite this as a logarithm, so I can get that y out of my exponent. Okay? So I'm going to switch to a new little page. So if we go to our b, y equals x, and we can go through and we can label all of these things. We refer to b as the base. We've always referred to it as the base. Our y is our exponent because it's up above. And then I usually just call my x, I just usually just call it a number. It's whatever it's equaling. I'm just calling it a number because we just got to name it something, right? So this is going to be equivalent to a logarithm. And when it comes to writing our logarithms, we would have y equals log base b to the x. So we just have to be careful when it comes to our notation. This b that is a base, it's like a subscript. So subscript means that it's written down. So it's going to be below the line. And then our x is going to be on that same plane as our log, right? And lo and behold, we can sit there and we can name all of these little parts from our exponential. So our y represents our exponent. Our b still is the base. and that x we refer to as the number. So we can very easily, since these are equivalent, we can switch back and forth between these two forms depending on what kind of problem it is that we're looking at and that we need to be working on. So let's write some equivalent forms. So let's start with write the equivalent. We'll go exponential first. Exponential form. So for problem number 1, we're going to say that we have 4 equals log base 2 of 16. So we just want to be able to convert this. It's written as a log, so we were a log and we want to write it as an exponential. So if you need to, go through and label all of your parts. This 4 is going to be your exponent. Right? Your 2 is your base, and your 16 is your number. So to write that equivalent form, we would have our base 2 raised to an exponent of 4 equals our number, which is 16. And on this one, we can even double check it. What's 2 to the 4th? 2 to the 4th is 16. Let's try one more of these. Let's say we have 5 equals log base b as in boy, of 32. So what's my base? B. What's my exponent going to be? 5, and that's going to equal 32. And we'll get into solving these in a little while. On these ones, I just want you to write the equivalent form. So you're not solving it for the variable, you're just giving it to me in the form. That way we know that we got our first steps of these problems, that we got a good grasp on them, so then we can move on to solving them. So now let's go the other way. Since we wrote these as equivalent exponential forms, let's go just the opposite. So we're going to write the equivalent logarithmic form. So write the equivalent logarithmic form. So for problem number 1, let's do a nice little 2 to the 3rd equals 8. And I think we all know that 2 to the 3rd equals 8. So it's a nice little problem to see when it comes to writing this back into our logs. If it helps, sit there and kind of write out those 2 little forms somewhere on the side on your homework paper and your notes that by equals x, that would be exponential, and then to write that as a logarithm, you would have log of base b of x equals y. Right? If it helps, just keep writing that over and over again until you get it down. So again, if you need to, write these down. This is your base, the 3 is your exponent, and your 8 is your number. So to write it in the form of a log, it's going to be log of base. What was your base? Your base was 2. Of what number? 8 equals your exponent, which is 3. Right? Alright. Let's try example number 2. Let's make it a little more fancy. And let's say we're doing the 3rd root of 8 equals 2. So we remember when it comes to our radicals, how to write our radicals as so that our exponent is a fraction. So if you need to, you can throw that 1 there as 8 to the first if you need to. So we can rewrite this as 8 raised to the 1/3 equals 2. And then when it comes to writing our log, we have the log. What is our base? Our base is 8. What's our number? 2, and that's going to equal 1/3. So these take a little bit of practice to kind of get used to. I think, but once you practice them a handful of times, it kind of becomes a little easier, a little second nature of how the whole routine kind of goes. We want to be able to evaluate some of these logarithms without using our calculators. We want to make sure that we have that conceptual understanding, so we need to make sure we know how to evaluate values. And we're going to do this without a calculator. Put a little smiley face on there, right? Alright, so problem number 1. Let's say we had log base 4 of 16 equals something. And we want to know what that something is, right? I always usually when they give you the problems, they don't give you the equal when they want you to evaluate it. I like to put the equals and put the little box in there. And it helps because on the top of my head, I don't have all of these logs memorized. Back in the day, you used to have pages and pages that you would go through to figure out what some of these values were. But we know how to write this as an exponential, so if I can write it as an exponential, it might help it be more clear on what my box is going to equal. So since I have a logarithm, I'm going to write it as an exponent. So my base is 4, and 4 is going to be raised to some number, my exponent, and that's going to equal my number, which is 16. So I have to try and figure out 4 to what is going to give me 16. How about 4 squared? So then I know that log base 4 of 16, I know that that's going to be 2. Let's say we have log base 5 of 1/5, and we're asked to evaluate that. So if we're asked to evaluate, we want to know what that's going to equal. So we're going to draw our little box. And again, I might not know off the top of my head what this answer is, so I'm going to write it as an exponential, So my base is 5 raised to some exponent is going to be my number, which is 1/5. So in order to get my 5 into the denominator, I have to change my sign on my exponent. Right now it's a positive 1, so I'd have to make that a negative 1. So then I know that log base 5 of 1/5 is going to be negative 1. Alright. In the previous section, we talked about graphing these logarithmic functions and being able to graph these without the use of our little calculators, right? So if we had f of x equals 2 to the x, and we want to graph this guy, I'm going to throw a little graph over here. Let me some values. Doesn't have to be absolutely perfect, but a good, decent representation, giving it a good fair shot, right? So we even went through and we made a table when it came to graphing this one. We had our x values, and then we had 2 to the x, which gave us our y values. So if I plugged in -2, 2 to the -2, we know it's going to give me a quarter. If I plug in -1, that's going to give me a half. If I plug in 0, 0, 2 to the 0 is going to give me 1. If I plug in 1, I'm going to get 2. If I plug in 2, I'm going to get 4, right? Then I can go ahead and plot these little points. -2 was a quarter, -1 was a half, 0 is at 1. That's an important spot. 1, 2, and 2, 4. So when I go to graph this guy, I get a cute little graph that looks something along this line. And when it came to our domain and our range, we knew that our domain is our x values. So when it comes to our x values, we're using all possible x values. There's no limitation. So we're going to go from positive infinity to negative infinity. When I look at my range, my lowest y value is I'm getting really, really, really close to 0, but I can't be 0. So I'm going to have a parentheses for my 0. And then my y is going to keep growing until I get to positive infinity, right? So at the very beginning of this, the question was, do exponential functions have inverses? And they do have an inverse, right? So we want to also be able to graph the inverse. So to find the inverse, you're going to switch the x's and y's, right? So we originally had y equals 2 to the x, and then now we have x equals 2 to the y. So now we got to figure out how to graph this guy, right? So same thing if we came up with that table. I think I can throw it in right here. So if I had x and then I have 2 to the y, right? So it's kind of written a little backwards. Two options. When it comes to the inverse, you're just switching the x's and y's, so you technically can switch those babies around. But we're going to kind of plug in a couple values. When it comes to having a number raised to an exponent, if I went ahead and I put in, I don't know, let's say I wanted to figure out when x was 2. Right? Figuring out that 2 equals 2 to the y, well, that one's not too hard. We can figure out that y equals 1, right? But sometimes these kind of get a little bit more tricky. So usually when I do these and my y is up in my exponent, I actually work on them backwards. I'm going to plug in my y value, and then that's going to tell me what my x value is. So I'm going to start off with, I'm going to put in -2. Ooh, I can't hold that baby down. I'm going to put in -2. And when I put in -2, 2 to the -2 is going to give me 1/4. When I put in -1, 2 to the -1 is going to give me 1/2. 2 to the 0 is going to give me 1. 2 to the 1 is going to give me 2. 2 squared is going to give me 4, right? So then now I can graph these points. So when x is a quarter, y is -2. When x is a half, we're at -1. When x is 1, y is 0. When y is 2, we're at 1. And when we're at 4, we're at 2. Right? So now when I go to graph, if I follow these points going up, I'm going to go this way. And then what's going to happen when I get close to my y-axis? I'm going to get really, really close, but I can never touch my y-axis. So I have another asymptote. And when we find these inverses are switched over that identity line where that y equals x. And that identity line goes right through that diagonal through here, right? Y equals x. And it goes into the third quadrant as well, right? So I'm taking my original function and I'm flipping it over that identity line, and I end up getting my inverse function. Anytime you want to find the inverse, you're always reflecting it over that y equals x line. Sound good? And then you can go through and you can figure out your domain and your range now for your inverse. Right? Whoop. Go back to purple. Right? So my domain is my x values. So my smallest x value that I'm getting to is I'm getting really, really, really close to when x is 0. I just can never have when x is 0. And then x is going to continue to go to positive infinity. And then on my range are my y values. And my y value, well, I keep going down this way, don't I? So my range is going to be from negative infinity. And it's kind of hard to tell because we're kind of, our rate of change is getting smaller and smaller as we're going up, but technically this line is going to keep growing up and up and up and up on really small increments, but it is going to continue to go up. So it's going to go towards positive infinity. All right. Real quick, when it comes to translations or transformations, these are they're the same processes that happen with all functions when it comes to transformations. When you want to move things to the right or to the left, or up or down, or shrink, or all of that good stuff. So if we take our parent function and we say that f of x equals log of some base of x of some number, and then we want to do some changes to these. So if I have my log base b of x and I want to add or subtract a number to that, it's not with the x, it's outside of the x. So we know that this is going to be a vertical shift. So in other words, up or down. If I have my log base b, but I have my, whoops, I don't want a 1 in there, just a c. If I'm adding or subtracting that c onto there, it's going to be a horizontal shift. So horizontal would be either left or right for that value of c. Right? If I had a negative log base b of x, I know that that's going to reflect over, reflect over the x-axis. Right? If my negative is on my x and not the beginning of the function but on just the x, I know that's going to reflect over the y-axis. Right? If I have log base b of base b of x and I have a number out front, a constant term out front, or a number out front, any number out front, and we know that c is greater than 1, we're going to get that vertical stretch. And if our number is between 0 and 1, we know that we're going to get that vertical compression. Right? And then if we take log base b and we put our c with our x, instead of these being vertical, they're just going to be horizontal. So if c is greater than 1, it's going to be a horizontal, we call it a shrink, I guess, making it kind of smaller. And if it is between 0 and 1, it's going to be a, can't spell today, can't write either, horizontal stretch. Right? So they can give you a parent graph, and then they might give you another example that follows one of these, and they're going to ask you to graph it, like how does it look compared to the parent graph. And as long as we remember all the transformations that worked for, these all worked for linear lines, they worked for quadratics, they work for any family of functions, it's going to work just the same when it comes to our logarithms. So as long as we know how to graph our first one, and we know how because we can turn it into an exponential and we can graph it, And then we can do all of our shifts and changes that we need to do, shifts and reflections.